This is section 4.5. It's called chain rule, which is the same as 14.4 in Thomas's textbook. If you remember from single variable calculuses, when y was a function of u and u was a function of x, how did we go finding dy dx? In other words, when we had a composite function, so y was a function of g of x, correct? And g of x was u. So in order to go from what? X to y, first we had to go through the u. You remember, right? So the derivative of composite function, f of g of x, which is also shown by this notation at x, is the derivative of f at g of x times the derivative of g at x. You remember that, don't you? In other words, the derivative, what? Of y with respect to x was dy dx times du dx. Okay, you remember this example. Y is equal to 3x squared plus 1 squared. How do we take the derivative of this in single variable calculus? We let u be 3x squared plus 1. So dy dx, du dx is equal to 6x. So when you do that, so this guy, when you replace the 3x squared plus 1 with u, you get y is equal to what? U squared. But dy du is 2u. So therefore, if you follow this formula, dy dx equals dy du times du dx, you get 2u times dx, which is du dx, which is 6x. So replace the u, what you decided u is going to be equal to, and lo and behold, you have the answer. Question is, we have many cases in three-dimensional space when it comes to chain rule. So I'm going to go through 3 of those cases. The first one is when z is a function of xy, but x is a function of t, so is y. So the question is, can you find the total derivative of what? Z with respect to t. Why do I call this total derivative? Because these are single variable functions. Do you see it? They are not partial derivatives. However, to find the total derivative of z with respect to t, I have to go over something called tree diagram, which really helps you to come up with a formula. So this is the key for this section. Draw a tree diagram. What does that mean? Notice z is a function of x and y. But x and y, they are functions of t. So draw this tree diagram. Because z is a function of multivariables, so these branches are what? Partial derivatives. But each of these guys are a function of single variables, so these are total derivative. So to find dz dt, I gotta multiply these branches and add the results. In other words, to find dz dt, I go partial derivative of z with respect to x times dx dt, plus partial derivative of z with respect to y times dy dt. Notice the formula comes straight from the tree diagram. So to take the idea home, let's take a look at this example. Z is equal to x times natural log of x plus 2y, but x is sine of t and y is cosine of t. So according to this formula right here, I need first to take the partial derivative of this guy with respect to x, so the y's are held constant. However, because I have x here and x in the logorand, so I have to use the product rule. So I go derivative of the x, which is 1 times this, that's what this is, plus derivative of partial derivative of natural log of x plus 2y, which is 1 over x plus 2y, right? Times 1, right? Times the first term, which is x. So the partial derivative of this guy is 1 over x plus 2y times the derivative of x, which is 1, but times the first term, which is x. So there it is. On the other hand, partial derivative of z with respect to y, we keep the x as constant, so this guy acts like a number, so it just goes for the right. But the partial derivative of this natural log with respect to y is 1 over x plus 2y times the derivative of 2y, which is 2. So therefore, I get 2x over x plus 2y. Then I follow this formula. Notice dx dt is cosine of t, dy dt is minus sine of t. If you follow the formula, this is the partial derivative of z with respect to x, dx dt, partial derivative of z with respect to y times dy dt. So that's the answer. That's the total derivative of what? Z with respect to t. Sometimes they want you to evaluate these derivatives. For instance, what would be the value of dz dt at t is equal to pi over 2? Well, the idea is I don't have any t's in my answer, so I need the corresponding x and y value for t is equal to pi over 2. That's okay. Remember, x was sine of t, y was cosine of t. Replace the t's with pi over 2. So t is equal to pi over 2 corresponds to 1 comma 0, meaning x is 1, y is 0. So if you go back to this, long equation, replace the x's with 1 and y's with 0, lo and behold, you get what? Negative 2. So that indicates the rate is decreasing. So z is decreasing at this rate with respect to time. The next case is when you have z is equal to function of xy, but x and y, they are also functions of two other variables, namely s and t. So in this case, because these guys are what? Multivariables, I cannot ask for total derivatives. So the question might be, what's the partial derivative of z with respect to s? What's the partial derivative of z with respect to t? Then again, the key is draw a tree diagram so you can develop your formula. Notice z is a function of x and y. But x is a function of s and t, so is y. So because these are all multivariables, so all the branches are partial derivatives. None of them are total derivative. So to find the partial derivative of z with respect to s, what you do, go from the top of the tree to the bottom of the tree and take the branches which they end with s, because you're trying to find the partial derivative of z with respect to s. So multiply what? The branches from top to bottom and add the results. So to find the partial derivative of z with respect to s, I multiply these two guys plus product of these two guys. Okay? To find the partial derivative of z with respect to t, I take these branches, the branches which they end with t. So I multiply these branches plus multiply those two branches, and there you have it. So example would be like z is equal to e to the xy times tan of y, but x is equal to s plus 2t, and y is equal to s over t, which we can write it as s times t to the negative 1. Find the partial derivative of what? Z with respect to s and t. Remember, these are your formulas. So you need to take the partial derivative of z with respect to x, with respect to y, x with respect to s, x with respect to t, y with respect to s, y with respect to t, and substitute in this formula which you came up with off of this tree diagram, and lo and behold, you get a royal mess, right? So the next idea, which I call it case 3, is like, look, the function, original function is a function of two variables, but each of these variables are functions of three variables, x, y, t. So obviously we have to use partial derivatives. In other words, the legit question would be, what would be partial derivative of u with respect to x, with respect to y, with respect to t? Then again, the magic formula pops from the tree diagram. U is a function of r and s, but r is a function of x, y, t. So is s. So to find partial derivative of u with respect to x, go from the top of the what? Tree to the bottom of the tree and what? Look for the branches which they end with x. So the partial derivative of u with respect to x would be multiply these two partials plus multiply these two partials. Respectively or similarly, partial derivative of u with respect to y, now go from top to bottom and look for branches which they end with y because you're trying to find partial of u with respect to y. So multiply these branches and add them up. Similarly, for what? Partial derivative of u with respect to t. Example of this, which I'm not going to do it because these are the formulas. U is equal to r squared plus s squared to the power of 1/2, but r is y plus x times cosine of t. S is x plus y times sine of t. Find the partial derivative of u with respect to x, y, and t respectively. So here are your formulas. Do you see it? So the next idea is, how do you go about what? Doing these derivatives implicitly. In other words, it's called implicit differentiation. Suppose you have a capital function f of what? Xy, but y is a function of x. Okay, this y is a lowercase function of x. So what you do then again, you can what? Draw the tree diagram. F is what? Function of xy. X is a function of x, but y is a function of x. So to do this, what you need to do is what? Take the derivative of x with respect to x, which is 1. Take the derivative of y with respect to x, which is dy dx. So therefore, because I'm trying to find what? Dy dx. So what I do, I go like this. Partial derivative of capital what? F with respect to x times 1 plus partial derivative of capital F with respect to y times dy dx equals 0. Solve this equation for dy dx and lo and behold, you have it. So the answer is negative partial derivative of capital F with respect to x divided by what? Partial derivative of capital F with respect to y. Case in point, suppose you were asked to find what? Dy dx for this implicit function. Notice the y cannot be solved. The equation cannot be expressed explicitly in terms of y. So you need to take the derivative as you go from left to right. If you use this formula, make sure you identify your capital F of x first. In other words, set this guy equal to 0. Now that's your capital F of xy. Follow this formula, which is like what? Take the partial of this with respect to x. Take the partial of the same expression with respect to y. Don't forget to multiply the answer by negative. That's one way. The other way, as I mentioned earlier, take the derivative as you go from left to right with respect to y. For instance, the derivative of y to the 5th is 5y to the 4 dy dx. Here I got to use product rule. Derivative of 1 is 0. And here I got to use product rule, right? And then I can what? Solve this last equation for y prime, and lo and behold, the answer is matched. So whether you use the formula or take the derivative from left to right as you see it, but don't forget, here and here you have to use what? Product rule. The answers come up the same. Similarly, if the capital function fxy is function of three variables, but z is a function of x and y, the formula is partial derivative of f with respect to x divided by partial derivative of f with respect to z. There is a minus sign. Similarly, partial derivative of z with respect to y is partial derivative of capital F with respect to y divided by partial derivative of capital F with respect to z. Then again, there is a minus. Case in point, what if you got this? xyz equals cosine of x plus y plus z. So set this guy equal to 0 so you can recognize what's your capital function fxyz is equal to, then use these two formulas to find the partial derivative of z with respect to x and y one at a time. Yes? Finally, let's finish the section with a rate of change problem. So in other words, where do I use chain rule? The radius of a right circular cone is increasing at the rate of 1.8 inches per second. So this is the cone. So radius is increasing while the height is decreasing, at the rate of 2.5 inches per second. At what rate the volume of the cone is changing when the radius at the instant of time when the radius is 120 inches and the height is 140 inches. So let's see what's given. What's given is a rate of change of radius is 1.8 inches per second because it's increasing, so it's positive. On the other hand, the height is decreasing at the rate of 2.5 inches per second. So you got a minus here. Do you see it? Decreasing. We are asked to find the rate of change of the volume. Rate of change means how fast the volume is changing with respect to time. So T is the time. But I know the formula for what? Volume of a cone, which is 1/3 of pi r squared times h. So here comes chain rule. Volume is a function of what? R and h, but both radius and height are functions of time. So these are partials, these are total derivatives because these are single value functions. Do you see it? So if I go from top to bottom, multiply the branches, add up the results, so I get partial derivative of v with respect to r times dr dt plus partial derivative of volume with respect to height times dh dt. So take the partial of v with respect to what? R. So you get 2/3 of pi r h from here times 1.8, that was the rate at which the radius is increasing, plus partial derivative of this guy with respect to h, which is 1/3 of pi r squared times dh dt, but remember height was decreasing, so it's minus 2.5 inches per minute, or second I should say. So if you kind of work this out and leave the answer in terms of pi, lo and behold, you get 8,160 pi cubic inches per second. So what does that mean? As the radius increases 1.8 inches per second, and the height is decreasing at the rate of what? 2.5 inches per second, volume is increasing at the rate of 8,160 pi cubic inches per second. What does that mean? That means the volume is increasing this much per every second. Thank you.